Hi folks, we're starting a new unit about chemical reactions, but before we talk about chemical reactions, we need to talk about matter and energy in general, and that's what we're going to do today. So as a refresher, we talked about this before in Module 1, but chemical changes are changes that change the identity of a substance, changes what the substance is. So atoms are somehow rearranged, old bonds are broken, new bonds are formed to create new compounds. For example, hydrogen gas reacts with oxygen gas to produce water. We start with hydrogen atoms bonded to each other. We start with oxygen atoms bonded to each other. Those atoms break apart. Those atoms break apart, and the atoms rearrange themselves in a new way to create a molecule of water. This isn't balanced. We haven't learned how to balance equations yet, but we're going to start with the same atoms that we finish with. A physical change does not change the identity of a substance. It does not change what substance you're dealing with. So for instance, starting with water, that is a liquid, and freezing it until it is solid water. We didn't change what the substance actually was. We didn't change its identity. It's water at the start, it's water at the finish. This is a physical change. Any kind of phase change. There is another kind of change that we learned about in Module 1, and those are nuclear changes. That's when you actually start with one kind of atom and end with a different kind of atom. You're changing the atoms by changing the nucleus. We covered that in Module 1, and we're not really going to revisit that again. What we're focused on here are differences between chemical changes and physical changes. So, how do you know that a chemical change is going on? There are particular signs that you can look for. First of all, if there's a change in odor or a change in color or a change in heat, those can be signs of a chemical change. Just a couple notes here. A change in color. This needs to be an unexpected change in color. If you take something blue and mix it together with something yellow, you expect the product to be green. That is an expected color change. Here I'm talking about an unexpected color change, like if you mix something pink with something colorless and all of a sudden it turns yellow. That would be a surprising color change. So I'm talking about something more than just an averaging of color. Another special note here. Just because you have a change in heat does not mean it is a chemical change. There are physical changes that involve a change in heat as well, and we will look at those in more detail. A sure sign that a chemical change is going on is if light is produced. So something like combustion, a fire, light is being produced, that is the sign of a chemical change. If you see gas bubbles and those gas bubbles are not the result of a phase change, then that is a sign of a chemical change. So what I mean by this is boiling water is a physical change. So not boiling water here. You see gas bubbles in the pan of water that you're boiling, but that's because of a phase change. If you see unexpected bubbles not due to a phase change, that's a sign of a chemical change. The last sign of a chemical change is the formation of a precipitate. A precipitate is a solid that is formed from mixing solutions together. Again, this is a solid that doesn't appear because of a phase change. It forms unexpectedly. So here, two solutions were mixed together, and now we have this kind of cloud of a green milky cloud here. That's actually tiny particles of solid being formed from mixing two solutions together. In order for us to understand chemical reactions, we need to understand how the particles involved in the chemical reactions behave. So we're going to look at the kinetic molecular theory. The kinetic molecular theory states that particles are always in motion. The kinetic energy of the particles increases as temperature increases. And kinetic energy is related to particle speed, so temperature is related to how fast particles are moving. All motion, all particle motion stops at 0 Kelvin. 0 Kelvin is the same as negative 273 degrees Celsius, and we call it absolute zero because you can't get any colder than absolute zero. All motion stops, and because temperature is defined around particle motion, you can't have less than nothing in terms of particle motion. Thermodynamics is the study of the transfer of energy as heat. Now, heat and temperature are related ideas, but they are different, and it's important to distinguish between the two. Heat transfers can happen during both chemical and physical changes. Okay, so heat transfers can happen in both situations. It's not just a sign of a chemical change, it happens during physical changes as well. So what's the difference between temperature and heat? Temperature, as I've said before, is a measure of the average kinetic energy of the particles in a sample. It's related to their speed. We use units of Kelvin in the SI system, and we can measure it directly. You can put a thermometer in something and measure its temperature. Heat, on the other hand, is the energy transferred between samples of matter because they have different temperatures. So heat is related to temperature, but it's not the same thing as temperature. Heat always moves from hot to cold. It always moves from a higher temperature region to a lower temperature region. Heat is measured in joules. The units are joules. That's the SI unit for all energy, and heat is a kind of energy. Heat cannot be measured directly. Heat has to be calculated using a different method. You cannot measure it directly the way you can measure temperature. Temperature you can measure using a thermometer. Heat you must calculate. So when we talk about chemical or physical changes and how heat transfers, there are two main categories of heat movement that we talk about. We talk about endothermic changes and exothermic changes. Endothermic is when heat enters the system. Look at that capital. I capitalized it to draw your attention to it. Both words begin with EN. Endothermic enters the system. Heat enters the system. And when I say system, I just mean the particular thing being studied. Whatever you're studying, heat is entering that thing, those chemicals. In an exothermic process, heat energy exits the system. Again, EX for exothermic and exits. If the system absorbs energy, then that energy has to come from somewhere. Energy cannot be created or destroyed. Where does the energy come from? It comes from the surroundings. And when I say surroundings, I just mean anything that isn't the system. If the system absorbs energy, the surroundings must release energy. Or vice versa. So you can reverse that statement. If the system releases energy, that energy must go somewhere. Therefore, the surroundings must absorb that energy. When we're talking about reactions that are happening in solution, in water, the most immediate surrounding then is the water. So quite often when we do chemical reactions, we're doing them in water, and we can measure the temperature of the water quite easily. So often water is the surrounding for a particular reaction. Again, I said this out loud, but here it is in writing. Energy cannot be created or destroyed, but it can change forms. Energy can go from potential to kinetic, or from kinetic energy to potential energy. So it can change forms, but you cannot create or destroy energy. Let's look at endothermic reactions and exothermic reactions in more detail. In an endothermic reaction, remember, heat energy is transferred from the surroundings to the system. Heat enters the system. So here are my surroundings, here's my system, and heat is entering the system. Because heat enters the system, the surroundings decrease in energy. They decrease in kinetic energy. And remember, kinetic energy, temperature is a measure of the kinetic energy of particles. So endothermic reactions feel cold. Basically, the heat got sucked in from the surroundings, and now the surroundings feel cold. In an endothermic reaction, the system, remember, it absorbed some heat energy, so the system increases in energy. And the way it increases in energy is it increases in potential energy. So, and we'll look at the heat of reaction in more detail in a bit, but the heat of reaction, which has the abbreviation Q, is positive. What I mean by that is when we go from the reactants at the start of the reaction and we move to the products at the end of the reaction, going from start to end is an increase in potential energy. So this difference here, the energy absorbed by the system, is positive. It's a positive change. Like if this value is 100 and this value is 200, we went up by 100 kilojoules. Notice that the products have higher potential energy than the reactants did. So again, what we're trying to capture here is that the system is increasing in energy, but on our previous slide, the surroundings were decreasing in energy, which is why they felt cold. When the energy in one location increases, that energy must have come from somewhere. That energy decreases. We're going to have the same discussion, but this time the focus is on exothermic reactions. In an exothermic reaction, heat energy is transferred from the system to the surroundings. Remember, this is our system. This is the thing that we're actually studying. It's the chemicals of interest. And heat energy is leaving the system. It exits for exothermic, exits the system. Because heat is going into the surroundings increase in kinetic energy. Kinetic energy is a measure of temperature. So the exothermic reactions feel hot. The standard example of an exothermic reaction would be something that's on fire. Okay, fires feel hot. Energy is leaving the log or coal, whatever's burning, and going into the surroundings so that the surroundings feel hot. In an exothermic reaction, the system, the chemicals that we're looking at, decrease in potential energy. So the heat of reaction is negative. Again, I'm going from my reactants at the start to my products at the end, and energy is released between the start and the end of the process. So again, if I just make up numbers here, 100 and 200, I go from having an energy level of 200 kilojoules at the start to 100 kilojoules at the end. The chemicals have lost energy, therefore the heat of reaction is negative. Products have a lower potential energy than the reactants because they have lost that energy and given it to the surroundings, which is why the surroundings feel hot. So these graphs that I've been showing you with these green curves, hills, these are called reaction pathway diagrams. So I just want to talk to you a bit about them because by looking at them, you should be able to tell if a reaction is endothermic or exothermic. These reaction pathway diagrams show potential energy, the potential energy of a system before and during and after a reaction. So time is on the x-axis. It's labeled reaction progress here, but that's just, progress is just another way of saying time. And then potential energy is on the y-axis. The heat of reaction, which I've mentioned before, is the net energy absorbed or released during a chemical reaction. You'll sometimes see this abbreviated Q, and sometimes you'll see it abbreviated delta H. But basically it's here. It's this difference between the products and the reactants. So you can actually calculate it from one of these reaction pathway diagrams. The Q for the reaction is going to be whatever the potential energy level of the products is minus the potential energy level of the reactants. Activation energy is another feature of the graph. Activation energy is the energy barrier that you have to get past, you have to overcome it in order to actually start a reaction. For instance, a gas cooktop doesn't just ignite itself. The gas that comes out of the cooktop is very combustible, it catches on fire, but you do need a spark to get the process going. That spark that you need, that's the activation energy you need to actually get a reaction started. So this activation energy on the graph, if it's the energy we need to get the reaction started, we think about the difference between going from reactants to the top of the hill. Once we get to the top of the hill, it's easy to roll down and get to products, but we have to get to this highest energy level first before the chemical reaction can proceed. So again, you can calculate from this graph what the activation energy of a reaction is by looking at the value at the peak of the hill and subtracting the energy level of the reactants. So the potential energy at the peak minus the potential energy of the reactants. Notice that both of the equations that I've given you here on the slide are the final position minus the starting position, final minus initial. So when I wanted to know the Q for the whole reaction, I did the end of the reaction minus the beginning of the reaction. When I wanted to know what's the activation energy, what's the highest energy that I need to reach, I did the peak minus the reactants. So it's always the final position minus the initial position for the particular calculation you want to do. Let's do an example. So here is a reaction pathway diagram, and I've labeled some numbers on it so that we can actually do some calculations. So how would I calculate the Q value for this reaction? What's the difference between the products and the reactants? Q is products minus reactants. I start at the end. So I'm going to start with a value of 60 for the products. 60 for the products. And I'm going to subtract my starting point, which was 120 kilojoules here for my reactants. 60 kilojoules minus 120 kilojoules is negative 60 kilojoules. The order is important because the sign is important. Remember that a negative Q value is a sign of an exothermic reaction. When products are lower in potential energy than the reactants were, that's an exothermic reaction. Okay, how about another calculation here? How do we calculate activation energy? We need to know the value at the peak of the hill, which is 300, minus the peak, minus the energy at the start of the reaction, which is 120. 300 minus 120 kilojoules is 180 kilojoules. Notice that this is a positive value. Activation energy is always positive because starting a reaction is always an endothermic process. You always have to put a little bit of energy in to get a chemical reaction started. So there are a few practice problems for you. You can pause the video and have a go. Hopefully you noticed that the products are higher in potential energy. Products are higher in potential energy than the reactants, and therefore that is the definition of an endothermic reaction. Question 2. Again, pause the video while you use the reaction pathway diagram to actually calculate the heat of reaction. Calculate Q. Q is calculated by doing the products minus the reactants in terms of their potential energy. And so my value of the products is 300. My value for the reactants is 100. And therefore my Q value is positive 200 kilojoules. I guess the units aren't listed here. We'll pretend they're kilojoules. Notice that the arrow that corresponds to the Q measurement on this reaction pathway diagram is arrow C here. It's the difference between the products and the reactants. Lastly, pause the video while you calculate the activation energy using this graph. Activation energy is always the peak minus the initial value. So our value at the peak here is 400 kilojoules, and our value at the beginning is 100 kilojoules. So our activation energy is 300 kilojoules. Notice that the arrow on the diagram that corresponds to this activation energy is arrow A here. I hope this helped.